Hi. Can you all hear me?
Yes, ma'am.
Yes, ma'am.
Yeah, fine.
Yes, ma'am.
Welcome. Yeah, good morning. So we will start the course in a minute. Okay, so in the last class, what we did is that we moved into torsion of non-circular shaft, which is given by Sandvenen's theory. Okay, so this is Sandvenen's theory, Sandvenen's torsion theory. Okay, just as a brief recap, what was said was that the only difference between torsion of circular shaft and torsion of non-circular shaft is that in torsion of non-circular shaft, there is an out of plane deformation which is given by this warping function psi x of y. Okay, so and we have seen that any warping function that satisfies these two conditions, the condition 1 and the condition 2, is an acceptable warping function for the shaft of any arbitrary cross section. So our job is to find out a warping function which satisfies equation 1 as well as satisfies the equation 2, which comes from boundary condition. So this comes from equilibrium condition. This is from equilibrium condition and this is from the boundary condition. So as I said in the last class, it is rather easier to find out a warping function which satisfies equation 1, but as can be seen from equation 2, it is a difficult task to find out a warping function which satisfies the equation 2. To circumvent this, a trick is adopted, which is called the Prandtl stress function. I guess you all have studied about stress function in the last course. So what we are going to do is adopt something called a Prandtl stress function. Okay, for easier solution of the torsion problem. Okay, so what does this Prandtl stress function states? So the stress function that we assume, is tau xz is equal to del phi by del x, sorry, del phi by del y, and tau yz is equal to minus del phi by del x. Okay, so don't confuse with this. This is not phi. Fiver's angle of twist. Don't confuse between the two. I have seen student, this is stress function. Okay, don't confuse between these two. Right? So phi was the angle of twist. This is actually the Greek letter is varphi. Okay, so the varphi is the stress function that we are assuming. So if this is the stress function, then I already know that tau x jet is equal to g theta del psi by del x plus y. And that is going to be del phi by del y. Similarly, tau yz is equal to g theta del psi by del y minus x, and that is equal to minus del phi by del x. Okay, right? So if my tau x is del phi by del y, then tau x jet can be written in terms of my warping function and again rewritten in terms of del phi by del x. Okay. Now, what I'll try to do is that I will from this two equation, from this equation and this equation, I will try to eliminate the warping function psi and try to get a relation on phi. Okay, let me do that. Okay, so if I have g theta del psi by del x plus y is equal to del phi by del y, and I have g theta del psi by del y minus x equals to minus del phi by del x. If I just take the double derivative, I take the derivative with respect to this and add this two up, I am going to get from this two expression, I'm going to get del 2 phi by del y square plus del 2 phi by del x square is equal to minus 2 g theta. Okay, so if I just do this from this two equation, if I try to eliminate the warping function psi, I am going to get an equation on phi of this form. Okay, so that is the first equation. Now let us see whether this this expression that tau x jet equals to del phi by del y and tau yz is equal to minus del phi by del x, are they satisfying the equilibrium condition? Whether this condition satisfies the equation of equilibrium. Okay, let us see. So let us go into the equations of equilibrium. So I have del sigma x by del x plus del tau xy by del y plus del tau x. So out of this, x is equal to 0, xy is equal to x is equal to 0, and then I have del tau x z by del z that is equal to 0. Okay, tau x z is equal to tau zx is equal to 0. So this whole thing goes to 0. Okay. Yeah.
There is a lot of lag, ma'am. Like, we're not able to see what you're writing, like, until so long after.
Okay. Okay. So I don't think I can do much about it. I'll just give it. I myself will give a lag. Okay.
Ma'am,
Yeah.
can you tell me why the third term is zero again?
Yeah. So see, the thing is that you look into the expression for del phi by, so tau xz is del phi by del y. Okay. And del phi by del y is again del phi by del x plus y. Okay. Phi is a function of xy, y is of course y. So del phi by del y is going to be a function of x and y only.
Okay, ma'am.
Okay. Okay. So now let me look into the second equilibrium of equations of equilibrium, where tau xy is equal to 0, sigma y is equal to 0, and tau yz being a function of x and y only, this also goes to 0, and y is equal to 0. So this goes to 0. Okay. Then the third equation of equilibrium, tau xz by del x, what is that? That is equal to minus, that is equal to del phi by del x del y. Okay. And what is tau yz by tau y? That is minus del phi by del x del y. Okay. And sigma z is anyhow equal to 0. Z is equals to 0. This two will also cancel each other. Sorry, there's a lag, right? So this goes to 0. Okay. So therefore, this assumption of stress function, or this form of stress function, Prandel's stress function phi, satisfies the equation of equilibrium. Fine? Yeah.
Ma'am, in last class, we found that tau xz was equal to g theta into d psi by dx minus y.
We used minus y, is it? Would
Yes.
be.
And the next one was d psi by dy plus x.
We have to check that. I mean, I can always. That is minus y. My wrong. Anyhow, nothing is going to change if it is minus or plus. I mean, nothing in the derivation is going to change. Is anything changing? My bad. This should be. Did I again did something wrong? So this is minus, right? Yeah. Is this okay now? Is anything changing because of this mistake? Nothing, right? In the derivation?
I think now it's fine, ma'am. Actually, previously it was, I think, wrong.
Okay, fine. Great.
Yes, ma'am.
So, fine. Thanks for pointing out. So, there it goes. Okay, so now we see that this stress function satisfies the equation of equilibrium. Okay. Now let us see whether it is satisfying the boundary conditions. I will talk after I write a bit so that this lag is somehow overcome.
Ma'am, can we have a recorded class instead, ma'am?
You
That would
want
be
me to record and then you present it? That's also fine. I can do that. I can do that. So
no,
maybe
like you can record and you can post on the Teams group, and we can have these as doubt sessions. These classes.
fine. That's what I'm going to do. Okay. So I will from next week probably I'll just record and post it. And then this interaction sessions will be just doubt clearing session. Fine. That's actually is good for me as well. So fine. So next class onward, this weekend I will upload the recording for the next week. Okay. Anyhow,
Sure,
let's
ma'am.
go ahead.
Thank you,
Go
ma'am.
ahead. Yeah.
Ma'am, what happened to the n component?
So the n component on the lateral surface is anyhow equal to 0.
Okay, because n is 0.
Yeah. So I'm not writing the entire boundary condition. This we have already seen for the previous class and previous to that, right? So I'm
Yes,
just
ma'am.
cutting short here, and we know that only this part is what is causing the problem, right? Everything else is equivalently 0. Okay.
Yes, ma'am. Okay.
So right. So in for this boundary condition, tau x check can be written as del phi by del y. L we have seen is dy by ds from the figure that I have drawn, and tau yz is del phi by del x, and m is equal to dx by ds. Okay, and this can therefore be written as d phi by ds. Okay. Now, what does this expression mean? This expression means that the stress function phi has to be constant along the boundary S. Okay, only then d phi by ds equals to 0. Now, we can conveniently assume the stress function phi to be 0 on the boundary. That is also going to satisfy the equation 2. Okay, I can conveniently consider phi equals to 0 on the boundary. So this is also going to satisfy equation 2. Okay, therefore we have to get hold of a stress function phi which is 0 on the boundary of the cross section. Okay, and it satisfies this condition that this condition 1. So I have to find a stress function which is a function of x and y, which is 0 on the boundary of the cross section and satisfies these two conditions. This is rather easy to find out. Okay, it's very easy to find out a function which is going to be 0 on the boundary. And of course, this is also an easy equation to solve for. So the approach of Prandtl stress functions allow us to find out a stress function in a much more easier way. And once we find out the stress function, we can find out the expression for the, and that is going to solve our entire problem. Once I know the expression for shear stresses, from there I can do anything that I want to do. Okay. Any questions here? Okay. Anyone has a question? Okay, now let us look into the boundary condition. So you have to keep these two in mind, expression 1 and expression 2. Okay, so we have seen from the previous example that the boundary condition that needs to be satisfied on the top and bottom surfaces, from the three boundary conditions that we have, what is left over is that the are these two conditions that needs to be satisfied on the top and bottom surfaces. This condition is that the the surface forces in the x direction should be equal to tau xz, and the surface force in the y direction on the top and bottom surfaces has to be equal to tau yz, both the magnitude as well as the distribution. And we have again said that though in real life cases it is not possible to, it doesn't happen that the moment is applied in terms of x hat and y hat, but it doesn't matter much because of Sentence theorem. The effect is negligible in the inner domain of the structure. Okay. Now what I'm going to see. So let me just draw the figure. So say this is the top surface. Okay, so this is how the surface forces and the top and bottom surfaces should be distributed in order to satisfy the boundary condition on the top and bottom surfaces. Now, what we are going to try to see is that if the surface forces, boundary forces on the top and bottom surfaces of the shaft is distributed in this form, the resultant forces are going to be 0. Okay, let me try to show this. The resultant of the force in x direction Let me call this as Sx. Okay, so is this okay? Do you all agree with this? That the resultant of the boundary condition forces on the top and bottom surface in x and y direction are given by this expression.
Ma'am, but isn't the resultant force over the entire surface 0?
Yeah, we have to see that, right? We have to see that it is 0 on the top and bottom surfaces.
Okay.
See, for circular cross section, it was pretty obvious that it is 0, right? Because it was arranged in a typical way.
And it was symmetric. Yes, ma'am.
It was symmetric, it was obvious, but here it is not that obvious. So let us see that it is 0. Okay. So now let me write this as okay. So now let us try to prove this. I have to okay. So if I write down the expression of tau xz in terms of my stress function, then this is the expression that I'm going to get. And then I do integration in this way. And by using Green's function, this is nothing but the integral of phi over the boundary with respect to dx. Okay. And since my phi is equal to 0 on the boundary, this is also equal to 0. Okay. Since I'm going to choose a stress function, I need to choose a stress function which is 0 on the boundary. It has to be this integral over the boundary of phi over dx has to be equal to 0. Similarly, Sy will also end up being the boundary integral of the stress function over dy, and that is also going to be 0. Okay. So we see that though there is a requirement of boundary forces on the top and bottom surface, the resultant of these forces are going to be 0. Okay. So if the resultant of the forces are 0, then the only thing that the forces are doing is to produce a moment. And the moment is going to be a torque, okay, a moment about the z-axis, right? So let us try to see what is the expression of moment about the z-axis. Is this part understood? Is there a question here?
Ma'am, can you go to the previous page?
I have erased that. Can you tell me which part you didn't understand?
Ma'am, actually I did not copy the last few lines.
I will upload the note. I have already uploaded the one for the circular shaft. This I will upload today.
Okay.
Okay, fine. So any question here? Anyone else has a question? Is this clear? See, this part is the most difficult part of the course. I mean, it might be sounding a bit difficult, but from once this module is done, then everything is pretty straightforward. It's like it's a very manual-like thing, okay? But it becomes straightforward once you understand this elasticity theorem that goes behind it, okay? So though this part may need some amount of thinking and some amount of understanding, but it's worth doing it because henceforth things will be pretty straightforward. It's just like a manual. I mean, it's just like if it is this, you do this kind of thing. Okay, so to make the rest part of the course manual like, you have to understand this part very well. Okay, so you have to bear with the complicated mechanics, the rather complicated mechanics of the torsion part before we move into the easier part. Okay, so don't get turned off by what we are doing right now. Okay, so
Ma'am,
yeah,
the Sx is 0 only because that phi function is taken as 0. Is it so?
yes.
If the phi function was anything else, then the Sx would not have been 0, right?
It would not have been 0. So there are examples where you cannot take a phi function to be 0. You cannot get hold of a phi which is 0. Okay, there are some issues that we need to handle. Okay.
Okay.
Okay, so maybe if we have time, we will do those examples, but right now I'm not very sure. Okay, fine.
Okay.
Ma'am,
Yeah,
the original condition is that phi should be constant on the boundary, right?
yes.
Okay.
So for
Ma'am,
yeah,
even if we take a constant phi, then also this integral over like phi dx will not be 0, right?
it will not be 0.
So we have to take it constant and 0 also, like equal to 0.
We have to take it 0, okay, because that is making our life easier. If you go ahead with phi to equal to constant, then also there are these conditions will be satisfied, but the derivation is slightly more complicated. Okay, so I'm not trying to get into that right now.
Okay, but the condition will be like the condition integral phi dx over the boundary will be 0 even if phi is constant and not 0.
Uh, even if phi is constant and not equal to 0. Okay.
Okay, ma'am.
Okay. Yeah, but phi equals to 0.
Ma'am, I didn't get that in the between.
Yeah. So see, what I'm trying to say is that even when phi is not equal to 0, okay,
Yes, ma'am.
we can solve the problem. Okay.
Okay.
But that is a more complicated version of it. There has to be some equilibrium, some other equilibrium condition coming into picture. Okay, so let's not get into that right now. There are examples which I usually solve in the class where phi is not equal to 0. For this time, if time permits, we will of course go into those examples and see if phi is not equal to 0, how can we handle the situation.
Okay. Okay.
Okay. So right now, let's be happy with the condition that phi is equal to 0, keeping in mind that phi not being equal to 0 is also an acceptable solution which satisfies the boundary condition and the equilibrium equation. So now that the resultant forces are zero, so from this we get to know that boundary forces okay. So that is what we can conclude, that the resultant forces are zero because of this boundary forces. So that the only thing that these boundary forces are going to do is give me a torque or a torsional moment. Okay, let me. Yeah.
Ma'am, but if we take phi as 0, then the first condition that we obtained, that del square phi by del y square plus del square phi by del x square is minus of 2g theta.
No. Phi is zero on the boundary.
Oh, all right. Got it.
Okay, so now let us see what is the expression for torsional moment. Yes. Yes.
Yeah, ma'am, that del square phi upon dy square plus del square phi upon dx square is equals to minus 2 zeta z theta.
Yes.
That should be like for each and every case, right?
For each and every case, as in?
Like you are saying that phi is zero on the boundaries. So, but this condition is not satisfied on the boundaries.
No, so I have to find out a phi which is zero on the boundary, and inside it satisfies this condition. So see, phi is going to be a function of x and y.
Yeah.
So I have to find out a function of x and y which is zero at the boundary.
Okay. Okay. Yeah. Yeah. I understand.
Okay.
Ma'am, here x is multiplied to tau, I think.
Yeah, y hat into x minus x hat into y, right? Is this okay? Have I written it correctly? I guess so. Yes, looks to be correct. Okay, so now what we do is that we do integration by parts.
Ma'am, how did you get this equation, the first one? Like call it.
This one?
Yes, ma'am.
Yeah. So so see, so on what do I have on the top and bottom surfaces? I have x hat and I have y hat. Okay. So they are trying to create a moment about the z axis. Okay. So the moment is y hat into x. X is the, let me draw the figure. Okay, right? So I am getting y hat into x is giving me a moment. Y hat is per area. This is also per area. Okay, so right, so the moment is y hat into x minus x hat into y.
Yes, ma'am. Got it, ma'am. Got it.
Right, okay. So if I do integration by parts, then this expression is going to end up something like this. Okay, I'm leaving the integration to y'all. I mean, it's very straightforward, right? I don't even, and you can say that if I do integration by parts of this, this is going to lead to this. Okay, so this again is the boundary integral, which is 0. This is the boundary integral, which is 0. So I am left with this. Okay, so therefore MT okay. So what does this expression gives me? Equation 3 relates, yeah,
Ma'am, why are those two terms 0?
because phi is 0 on the boundary.
And this phi dx dy is 4.
So I'm doing integration by parts. So if I
Okay.
do integration by parts, I'm taking phi. So my this integral is becoming boundary integral.
Okay, okay.
So now from equation 3, I get a relation between the applied torque MT and the stress function. Now, why is this? Let us understand this. So I have to get hold of a stress function phi, which is going to satisfy equation 1, and it is going to be 0 on the boundary. So if I get hold of a function phi, I know the expression of, so function phi is going to be a function of g, and g, that is the shear modulus, and theta, that is the rate of twist. Now, once I know phi, I know the shear stresses. And from expression 3, I know the applied moment. So this expression 3 is going to relate MT with okay. So from this expression, if I know phi, I can relate the MT, that is the applied torque, in terms of shear modulus G and rate of twist theta. Okay, if I'm able to relate the externally applied moment MT in terms of theta and G, then I can get the torsional rigidity, right? You have done that in your first year class, that the applied torque is equal to shear modulus into the polar moment, into the polar moment of inertia J, or what is that called? Yeah, J, IP or J, and into theta, right? So this relation gives me the torsional rigidity of the bar of any arbitrary cross section. is that clear? Anyone has any question?
Can you please explain this once more? I could not get it completely.
See, let me go on stepwise. How am I going to solve the torsion problem of an arbitrary cross-section shaft? Okay, I will know the cross-section of the shaft. I will find out a stress function phi, which is going to satisfy the two conditions. It is going to be 0 on the boundary, and it is going to satisfy del 2 phi by del x square, that one. Okay. So once I get hold of phi, which is a function of theta and g, then I can read.
I do not understand this one. How is phi a function of theta and g? How are we getting that?
So phi is a function of theta and g because of this, right?
Right.
I will have to have g and theta in my phi. Otherwise, I'll not be able to satisfy this equation.
Okay.
Okay. So therefore, phi will contain g and theta in it, and a function of So okay, right? So phi is a function of g, theta, x, and y, right? So therefore, this mt will be expressed in terms of okay. So therefore, I can get my applied torsional moment, applied torque as some g theta into j. So j is nothing. So this whole thing is nothing but okay. And therefore, this whole thing is going to Gj is the torsional rigidity. Is this okay?
Yes, ma'am.
Yeah. Okay. So fine. So then, yeah.
Ma'am, is applied torque a function of g theta and j, or is it directly equal to g theta into j?
This is equal to g theta into j.
Okay, okay.
Okay. So, so that's how you are going to get the torsional rigidity of the rod. See, these things will get very clear when we solve certain examples, which we are going to do in the next class. Okay. So, right. So, any questions here? Okay. So let me just summarize the whole thing. So, summarization is tau xz is del phi by del y, and tau yz is torsion of non-circular shaft. Okay, so similar to your torsioner of circular shaft, even here there is no in-plane distortion, okay, or in-plane deformation of the cross section. So for circular shaft, it was rather easy to perceive, but here I leave this to you as an exercise. You have to come and tell me why do you think that there is no in-plane distortion or deformation of the cross section. The clue is look into the stress and strain component and tell me in the next class, any one of you, okay, that why do you think there is no in-plane distortion or in-plane deformation. The displacements are given as u equals to minus theta what? Minus theta yz, v is equal to theta x z, w is equal to theta psi x comma y. Okay, so now from this is your job to tell me why there is not going to be any in-plane deformation or distortion, even in the case of torsion of non-circular. Okay, so with this I am done. So what we are going to do in the I will send an email about a quiz on Saturday 10:30. Okay, maybe 10:35 or so. It will be for this quiz will be a multiple choice one because I have yet not done any tutorial. You will not be able to solve numerical example unless I do tutorials. Okay, which we are going to do in the next week. Okay, so this week it is just going to be simple multiple choice question for half an hour. So there would be a strict half an hour duration in Moodle within which you have to answer the question, and the link closes by 11:05. Okay, so if there is any question, please let me know. Anyone has a question? Okay.
Ma'am, what is the portion for this quiz, ma'am? Syllabus?
Syllabus is, so see, it will be mostly theoretical question. There would be no numerical. So whatever I have taught till now, okay, I will upload the notes in Moodle.
Okay, ma'am.
Okay, numerical question will come only from next week onward. And I need a consensus opinion about whether you want a recorded lecture. Maybe your CR Pranav, you can just let me know. And there are two things that I need to know from you. Whether the lecture should be recorded or live, and whether the tutorial should also be recorded. So tutorials are going to be like this. I'm going to solve some examples. Okay. So it's mostly one way because you cannot solve right now. And so I'm just going to solve some examples. So I need to know from Pranav whether the lectures should be online. The lectures should be pre-recorded, and whether the tutorial should be pre-recorded. Okay, so Pranav, please let me know by a day or two so that I can plan over the weekend. Okay, so thank you. Thanks a lot. Thanks a lot. Bye. Yeah.
Now we were thinking instead of like you pre-recording and sending it to us, maybe you can pre-record it just so that this lag and all of that doesn't happen, and you can like play it during the class hours, and like whenever we have doubts we can pause. Like that's what some teachers or some other professors are doing.
Sure, I can do that. Of course. Fine. Just Pranav, just let me know. I mean, you please talk to everyone and just give me a email, okay?
Yes, ma'am. Sure, ma'am.
Whatever mode you want to, you just let me know. I will work accordingly. Okay, fine.
Okay, ma'am.
Yeah, thank you. Thanks a lot.